Okay, let's see this example. Y to be e to the x. The curve is y equal to e to the x from 0 to 1, x from 0 to 1. We rotate the thing about the x-axis. Rotation. So find the area of the surface. The surface is generated by rotating the above curve about the axis. The area of this surface generated by rotating the above curve about x-axis. The x-axis. X-axis. Okay. Now e to the x. When x is 1, when x 0, y is 1. When x is 1, e is y is e. E is a 2.7. Remember, e is 2.718, etc., etc. So it's around 2.5. Okay, e is around here. Okay, so this curve looks like this. Okay. Okay, somehow looks like this. Y equal to e to the x. Now we rotate it with respect to the x-axis. X-axis. Then what we get is this thing, okay, x-axis. So this we get x-axis. This x-axis. X, y. Okay, so this surface that we get. Now we find its area. Okay, A is, so we cut perpendicular to the x direction. Okay, perpendicular to the x-axis. So we use 2 pi times y times arc length element. Then we integrate from x to be 0 to 1, 0 to 1. Okay, so this is the x from 0 to 1. 2 pi y, what is y? Y is e to the x. Now ds, we need to find ds. ds is dx squared plus dy squared. Now if you factor out the dx, so this is 1 plus dy over dx squared times dx. dy over dx squared, this you get, y is e to the x. So this actually, dy over dx is invariant e to the x squared, 1 plus that dx. So this will be 1 plus e to the x squared dx. Okay, so this, if we so this will be of the form. Now if you let t be e to the x, let t be e to the x. So this will be when x is 0, this is 1. When x is 1, t is e, so this is e. 2 pi. Now e to the x times dx gives us dt, so this is dt. Now 1 plus the square root of the thing will becomes 1 plus t squared. Okay. Actually, we did this example. How did we use substitution again? We work out this example. 1 plus, remember, we did this 1 plus x square root dx. What we substitute is we let t be, the three cases of trig substitution. A squared plus x squared, a squared minus x squared, x squared minus a squared. Remember? Now a squared plus x squared, what do we substitute is let x be a tangent theta. Okay, so let t be tangent theta So 1 plus t squared, this will be secant squared theta. dt will be secant squared, sorry, dt will be secant squared d theta. So this will be, remember this will be, A will be, if we do substitution, this is 2 pi. Don't forget this upper limit, lower limit for this moment. So this will be square root of 1 plus t squared. This gives us secant theta, okay? dt gives us secant squared theta, d theta. Okay, so this actually turns out to be 2 pi secant cube. Sorry, one note just collapsed. Okay, sorry. dt will be dt will be dt will be secant squared of theta d theta. Then a will be, forget about 2 pi, 2 pi. Forget about the upper limit, lower limit. So this will be square root of 1 plus t is secant theta times secant squared theta d theta. So this will be 2 pi secant cube theta d theta. And we find its antiderivative, remember we find its antiderivative. This is we did this a couple of times. So its antiderivative is 1/2. You check your notes. Okay. Now what is upper limit and lower limit? Now t is from 1 to e. T is from 1 to e. Okay, t is from 1 to e. Now t is tangent theta, so t is tangent theta is from 1 to e. Okay, then so theta, tangent theta is from 1 to e. So how about secant theta? Secant theta is 1 plus square root tangent squared, t squared. So this is from square root 2 to 1 plus e squared. Okay, so this, so subtract theta 1, theta 2. So this you plug in, so this is 1/2 times 2 pi, you get a pi. Plug in when theta 2, then you get tangent theta is e, secant theta is 1 plus e squared, square root. This is the square root of 1 plus e squared times tangent theta is e, okay? Now ln, this is the square root of 1 plus e squared plus e. Minus tangent theta is 1. Secant theta is square root 2. Minus ln tangent theta is 1, so it's root 2 plus 1. Okay, then we are done. Okay, then we find the area of the surface. Okay. Okay, let's do this example. The ellipse. Let's do the ellipse. So suppose we have an ellipse. Okay, so here E is greater than B. Okay, remember last time we mentioned one time, it's not easy to find its arc length. Still remember what we did last time? How to find its actually really tedious. it's very difficult to find its arc length. So if you plot it, so it will look like this. It's an ellipse, more or less like this. So negative b, this is b, this is negative a, this is a, for instance. Okay, arc length. Remember arc length. So this is the twice arc length. Twice negative a to a. This times this thing 1 plus dy over dx. We integrate the arc length element. Remember, this is turns out to be a classical problem. Let's see. I think I did this last time. Did I did it? Let me see. I think I did it last time. Yes. Here is the arc length of an ellipse. Arc length of an ellipse. So we write, we use implicit differentiation to find dy over dx, and then we find arc length element. Then we finally need to evaluate this integral. If you substitute y by a function of x, then what it essentially is, you need to evaluate this integral. This turns out to be really, really important in modern mathematics. Now it's puzzled the people for around a century. In the 19th century, many research is actually devoted to this area. And even today, there are still many unsolved problems in this area. Okay. Although we cannot find, an analytic solution explicitly find its antiderivative. This one. Now we can actually do. If we do rotation, it will be another story. If we do rotation, find the area obtained by rotation. Okay, so this is the arc length. Now here we rotate a little bit. Rotate with respect to x-axis. Rotate with respect to the x-axis. So this is x. This is y. Okay. We rotate the thing with respect to x-axis. Okay. So what we get is, the thing is called an ellipsoid. Okay. So this will be, looks like this. So if you rotate it, so this will be okay. So it will be, looks like a foldable. Okay. Looks like a foldable. Okay, now how do we find, so this is called ellipsoid. Now find the surface area of this ellipsoid. Surface area of this ellipsoid. Okay, now how do we work out this problem? Find this ellipsoid. Well, we For this example, we preserve the symmetry, so we cut along the x-axis. Okay, we cut perpendicular to the x-axis. Okay, cut perpendicular to the x-axis. So what do we get? The surface area A is 2 pi y. Okay, 2 pi y. Then we use arc length element. This we get 2 pi y is, remember, y squared over b squared. You move terms x, y over z. So y is b multiplied square root e squared minus x squared over a. So this is y. Very easy to solve. So this is the solve in terms of x. B over a square root a squared minus x squared. ds is, what is ds? ds is dx squared plus dy squared. Okay, so ds will be a little complicated. Actually, we get the arc length element last time. So you check your notes. We get the arc length element last time. So the arc length element, if you factor dx, remember we have how do we find dy over dx? We again use implicit differentiation. Okay, use implicit differentiation. So y squared is b squared minus y minus x squared over a squared. So if you differentiate it, so you get 2y y prime, then you get b squared negative 2x x prime with y a squared. So you get y prime, which is negative b squared x over a squared of y. Implicit differentiation. Implicit differentiation. Then you get a y prime. Okay, so this will be y plus, take square, b squared x a squared y squared dx. Okay, so this will be ds will be y plus b power 4 x squared a power 4 y squared dx. Okay, so finally we substitute it back here. So this square root y plus b power 4 x squared a power 2 a power 4, sorry, a power 4 y squared dx. X is from negative a to a. Okay, so finally then we needed, let me just copy it here, the integral. So here we need to evaluate a is negative a to a, 2 pi. Now you can, all this you can factor out, b times a squared minus x squared. Now y squared, you can substitute y squared. Okay, you can substitute the y squared. It's complicated now. Complicated. So if you factor out a power 4 y squared, then what you get is a squared of y. Did I miss something? Yeah, it's easier. It's just a little ugly to do this manner. Yeah, so sorry. This is simply just y. We don't want, we let's do it in this form. Otherwise, it confuses yourself. So this is 2 pi y. Yeah, it's 2 pi y, and this will be okay now. So this will be a power 4 y squared plus b power 4 x squared dx. Okay, so finally you can cancel y. Finally, you get this is this cancel y, cancel y. So this is 2 pi over a squared negative a to a square root a power 4 y squared plus b power 4 x squared dx. And then you substitute y in terms of x. Remember, y squared is b squared y minus x squared over a squared. Okay, So it's complicated a little bit, but it's still doable. Negative a to a. So this will be a power 4. Y squared is b squared y minus x squared over a squared plus b power 4 x squared dx. So this will be 2 pi over a squared negative a to a. So if you rearrange this, so this you get a power 4 b squared minus b squared over a, b squared a squared x squared plus b squared x squared dx. Okay, so this will be, okay, so this factor out of b squared x, b squared 4. This will be, here we are calling factor b everywhere. Okay, so we can factor out b. So factor out b, b put it here. So this will be negative a to a. So this will be a power 4 minus a squared x squared plus b squared x squared dx. Okay, so finally, so this is got 2 pi b a squared negative a to a. So this is the a power 4. This will be plus x squared minus x squared, a squared minus b squared. Remember, a is greater than b, a is greater than b. A squared minus b squared is c squared. For this ellipse, we have the c is defined as b squared minus a squared minus b squared. So this dx. So this will be 2 pi b over a squared negative a to a power 4 minus c squared x squared dx. Okay. Okay. So you see, this is, what is this? You can use substitution. We can use substitution. This thing is, let's see. Yeah. You can work out this by substitution. Then remember, this is so if you do this, y minus x squared dx. Okay, we did this. So this is let x be sine theta. So this will be cosine theta d theta. So this will be y half cosine squared. Sorry, cosine squared will be half angle formula. Cosine 2 theta d theta. Okay, so this antiderivative will be y half of theta minus a quarter plus a quarter sine 2 theta. Okay, so this is the y half arc sine x plus this is the y half sine theta cosine theta. So this is the y half arc sine x plus y half x times square root of 1 minus x squared. Okay, now to find this antiderivative, a power 4 minus c squared x squared dx. Okay, so we let x be, we factor out a little bit. So if you factor out this a squared, so this a squared, this will be y minus a squared cx squared dx. Okay. This will be let t be cx over x squared. So this will be dt will be c over a squared dx. So this will be a squared over c times dt. y minus t squared. Okay, so this will be a power 4 over c arcsine t, arcsine of t. T is cx over x, the thing, plus 1/2. This complicated. X is t is cx over a squared times y minus cx over a squared. Okay, so finally, then we can evaluate. Okay, evaluate the thing from negative a to a. Okay, negative a to a, negative a to a, negative a to a. Then what we get is so this is all the function here. This is all the function. So this is then we get a to the power 4 c times twice that thing, twice cancel this 1/2. So the arcsine c over a. This number is called e. X is a, so this is a c over a times y minus c over a squared. Okay. So it's a power 4 over c. This is the arcsine e. So this number e is not the natural base of the natural log. So this e is characterized in an ellipse. Eccentricity. This is 1/2 of so this is no longer just 1/2 anymore. So it's e y minus e squared. Here e is c over a. E is c over a. Okay, finally you see we get our complicated expression. So this number multiply this number. What did I think I got a mistake somewhere? This c is common. This c is common to everything. Okay. Okay, finally we multiply the factor. Okay, so then we multiply 2 pi b over a squared. Multiply a power 4 c times arcsine of e plus e times the thing. Okay, so finally we get this is the 2 pi a squared b over c times arcsine of e plus e y minus e squared. Here e is c over a. C squared is a squared minus b squared. Finally, we're done for this problem. Find the surface area of this ellipsoid. Okay, find the surface area of this ellipsoid. Now this we can use, integration technique to work it out. However, the case we cannot. The case for arc length for ellipse, unfortunately, we don't have any. We don't have, an explicit antiderivative of that thing by elementary functions.
Okay, go back down.
This part, yeah. So we are done with the area of the ellipsoid. Okay, this topic is actually a really good topic for writing project. For the ellipsoid ellipse, if you want, try to write an essay, write a writing project on this arc length of ellipse. Okay, writing project. It's a good writing project. Write you know, arc length of an ellipse. This is a really good topic. You can try to Google search the history of this arc length of ellipse. So it's really important. So it opens the door to many important subjects in mathematics. If you write, if you do a writing project, it will actually introduce you to many beautiful mathematics. So I suggest you to write this writing project on this. All right. Any questions? Any questions?
So for the writing project, do you want us to write about like the history or something?
Can you say it louder?
What do you want us to do for the writing project then?
The writing project. This, you are asking about the ellipse or not?
So
Yeah.
you want us to write an essay?
Yes.
About like the history?
Yeah. Try to write, do some search of the literature. Search a little bit of the literature of arc length of ellipse. Okay. This is really important and beautiful branches in mathematics. Okay. Elliptic. This is related with something called elliptic functions. Elliptic functions. Okay. This turns out to be really beautiful, and it is of one of my favorite topic, elliptic functions. It's beautiful. Many mathematicians believe this is the most beautiful part in mathematics. Okay, I hope you can enjoy it once you do some literature, search some literature on this topic. Of course, you can. Question?
How many words do you want us to write?
How many words? I don't give you no upper bound. No upper bound. I don't restrict you to upper bound. You know, the lower bound is hard to set a lower bound. Try to, you know, when you do something, especially in mathematics, people prefer short. Once you write certain thing in one line, that's the most beautiful thing. You can write down a proof in one line, just a one line proof. That's perfect. As long as you just coherent and logical, you can try to be short. I don't give you an upper bound or lower bound. You just try to write an essay that is coherent, logical, and make this clear. Okay, make this question clear. You may think this, write the thing for yourself. Okay, once you have this kind of problem, how you solve this problem, how other people solve this kind of problem, what kind of idea to solve this kind of problem. Yeah, it's kind of an open problem. It's different than, you know, I give you a homework problem and then you work out, find a solution, you are done. Okay, then you are giving some formula, use some formula. For this kind of open problem, huge problem, usually that one don't have an easy solution. Usually one needed to do some literature search and organize the ideas that what other people did and how it works and why it doesn't work, or etc. like that. Okay, so it's a good training. It's a good training to do this kind of writing project.
Do you want to show any like mathematical computation?
Mathematical computation, you know, it's without any mathematical computation, it's hard, I think. You know, at least we should be logical and we should have a little, you know, computation, how other people computed it, you know, how we set up the integral. Yeah. Actually, we already did a lot of work. In our example, I told you how to set up the integral and it's easy to set up the integral because the formula is there. Okay, here is a formula. Then let's set up plug in the numbers, plug in the function explicitly, and let's work out the thing. Okay. That part is easily doable. That's doable because we already did the work. And do a little literature search on how people actually to evaluate why it's difficult and how people actually try to evaluate this kind of integral. Yeah. All right.
What's the due date of this writing project?
Writing project. Maybe you know, I should give you enough time. Like 3 weeks. 3 weeks. You can give me like May the 3rd. Yeah.
Okay, and how many those kind of writing project we may have?
How many writing project? You know, right now we do not have final anymore. We don't have final anymore. So we will use writing project as a form of final. Try to do the best you can. Do the best you can, you know, to the best you can. Once you write a qualified, really good quality, a writing project with really good quality, then you should get really high score. Then you should get a really good, reasonable score. Then this should be serve as your final. How many writing projects? You just do whatever you feel comfortable. My philosophy is the more the better. The more the better. Okay. Any other
critical on this, right?
Sorry?
Are you gonna be like critical on like the grading scale?
The grading? How you ask how I grade this writing project?
Yeah.
Writing project. It's really hard to tell you the standard how this, you know, a good quality, a writing project with good quality, you know, you should devote a lot of time and effort on it. So a good writing project should be, first of all, it should be logical, coherent, and also you should have some material. You should have some material, not too boring, You know, if you just read it yourself, if you find it's interesting, then for me, I will also find it should be interesting. If you see this is boring, then it should be, you know, also boring to me. Yeah. This is really good writing, good topic to do some writing on this. If you have any question about this project, you can talk with me. Let's do some literature search. Now, you know, in this course, it's very easy to learn something new. You know, find something in a textbook or, you know, attend a lecture. Once you have some open problem, it's another story. How to organize information, how to search the literature to get whatever you want. That's another ability that you should learn in a course. It's totally different than doing homework problem. But it turns out to be really important for everyone. All right, we have a couple minutes. Now let's start a new topic, chapter 10. Now chapter 10 is the last chapter of this course. Okay. In this chapter 10, we will start curves. Let me start a new book. All right. Okay, chapter 10 is about parametric equations. Chapter 10. So this is chapter 10. Chapter 10. Parametric equations. And the polar coordinate. Polar coordinates. Okay. Okay. First of all, we will study curves. Curves defined by parametric equations. Okay, first we define a plane curve. So what is a plane curve? So this is actually we introduce a little bit about the theory of plane curve. Okay, a plane curve is a collection of points in a continuous manner. Okay, on a plane. So a plane curve. C is a collection of points. X, Y. Obtained in a continuous manner, gathered together, obtained in a continuous manner. In a continuous manner. In a continuous manner. So a plane curve. So suppose, you know, we can just draw a plane curve. Okay, X, Y. So it has a collection of points on it. Okay, collection of points on this thing. Now, how do we give a curve? Now, to give a curve, then we should describe all the coordinates of this curve, all points on this curve, okay? I.e., we need to describe all pairs of x, y that is on this curve, okay? So, i.e., we should describe all pairs of relations of x and y, i.e., we should find relations of x and y. Okay, in certain cases, the relation can give directly. For instance, in certain cases, the relation between x and y can be given directly. The relation between x and y. So a point gives you a, you know, x, you get a y, okay? It's a, you know, a map. The relation between x and y can be given directly. Or explicitly. As, you know, for instance, y to be fx. Or, so here this, we get a function of y in terms of x. Or x as a function of y x to be gy. Now sometimes we don't have explicit, you know, sometimes we don't get explicit relation between x and y. It's hard to find the explicit relation between x and y. So we may also have implicitly, okay, or we give it implicitly in this form, fxy to be 0. Okay. So to give a curve, we need to give a relation between x and y. Okay. So sometimes we have explicit thing, x equals fx, y equals fx, or x equals gy. So this is explicit function. Or sometimes we have implicit differentiation. Okay. In what we did in implicit differentiation is we have an equation between x and y. Okay. Now we use another method. We introduce a new variable, new method. We describe the relation between x and y by introducing another variable. Okay, so new method. We do this. Okay, now the relation is between x and y. Okay, x and y, x, y. The relation between x and y. Now suppose we use another variable t. So we let t to determine x. If t can simultaneously determine x and y, then t determine a pair of x. Okay, for one t, one it can determine uniquely x equals x of t, okay, or you use f equals ft explicit, y equals gt, y equal to gt, okay. So then you can determine x and y. Once you determine x and y, then you determine a point xy. So this gives a point, a pair of a coordinate, a pair of point with coordinate xy on a curve. Okay, the idea is as we choose one t, so we get 1 point. As we choose another t, so we get another point. Maybe for instance, we choose another. Okay, so maybe t here we determine a point xy. Now another t we determine another point. Another t we determine another point. So finally we use t to determine any point on this curve. Determine any point on this curve. So t is changing. Okay, t is changing. So xy equals ft dt. Okay. So we get a relation between x and y by the function, by the variable t, by the variable of t. Okay. Now for example, some special case, x simply just t, y equals gt. Then what we get is this substitute t by x. So this is actually we get y is gx. So this curve is simply a graph of a functions. Okay. So this is the curve, graph of a functions. Graph of function. The curve is actually a graph, simply just a graph of the function y equals x. So this is actually the graph of y equals x. Okay, more example. Now this is actually a trivial example. T is from 0 to 2 pi. Now what this curve is? What is this curve? Okay, this curve this curve is simply the unit circle. Unit circle. This is the unit circle. Remember, if we have a unit circle, okay, remember if we have a unit circle, now this angle is t. This angle is t. This angle is t. Now what is the, so this is the x coordinate. And this is the y coordinate. This is the y coordinate. Okay, the point P, sorry, let's use Q. It's more standard to use Q. Now, so the hypotenuse, the radius is 1. So it's a unit circle. Unit circle. So any point on the unit circle is determined by the central angle. Any point Q is determined by the central angle. We start from our point, let's use A. Okay, this is the O. Once you know AOQ, the angle AOQ, the central angle, then you actually determine this Q uniquely. Okay, suppose the angle is T. Suppose the angle is T. Then how do we determine Q? Now you can determine the coordinate of Q, X and Y. Okay, by solving triangle. By solving triangle, then you find Q. X coordinate of Q is cosine of T. Y coordinate of Q is sine of T. By solving right triangle. By solving right triangle. So you see, as T changes varies from 0 to 2 pi, then this point as T increases, then Q travels along the circle. Okay, Q travels along the circle as T increases. Q travels along the circle once. Okay, travels along the unit circle. Once, one round as T, T runs through 0 to 2 pi, 0 to 2 pi. Okay, so this gives the thing, the Q, the point Q, chase out the unit circle. Okay, so this we get an equation, parametric equation of the unit circle. Okay, so this gives a parametric equation. Parametric equation of the unit circle. Of the unit circle. Okay, you can also check that x squared plus y squared. X is cosine t, cosine squared plus sine squared. Y is sine squared. X squared plus y squared is 1. So this is actually the equation for the unit circle in xy coordinate. Okay, now this unit circle is a geometry figure. It's geometry figure. Another important thing that mathematicians actually want to solve is, once you have some geometry figure, now do we have some special point on this thing? Okay, we will use this parametric equation, try to solve a number theory problem, i.e. question. Find all rational points. So rational points on on nice curves, on circles, on some geometry figures. Okay, this is a huge topic. Okay, this is called arithmetic geometry. arithmetic geometry. Right now, there are many open problems in arithmetic geometry. This is a branch of number theory. So this is a subset of number theory. Subset of number theory. Okay. The idea is the following. The idea is the following. Let me just mention a little bit the idea. Now the idea is okay. Suppose we have a circle. How do we find a rational point on the circle? First of all, we have 0, 1, 1, 0. This is trivial. This is called trivial rational point. Okay, so the idea is the following. From this -1, 0, this point. Now, if you do rational, this is a rational point, this x, y is rational. Then, if you connect the slope, the line L has slope, rational slope. Okay, rational slope. If x, y is a rational point on x squared plus y squared equal to 1. The unit circle. This point, let's use P. Let's use it again Q. Let this point be, let's use this PQ. Then KPQ is rational. Conversely, this is also true. Conversely, this is also true. If KPQ is rational, then Q is also rational. Okay, Q is also rational. Conversely, this is also true. This is also true conversely. So, to determine a rational point on this thing, on the circle, it is suffice to find PQ such that PQ has rational slope. Okay. Now, if you let me finish this. Let me mention a little bit. Remember Fermat-Last theorem. Now this actually Fermat-Last theorem. Find the right integer solution is actually you just now this square x squared plus y squared equal to z squared. This n equal to 2. Okay. This is what we are trying to do right now. N equal to 2. Now n equal to 3 or something. This is called Fermat-Last theorem. Fermat-Last theorem is puzzled people 300 more than 3 centuries. Okay. Now this case, square case turns out to be easy. Now we don't have enough time to deal with the square case anymore. Next time we will describe how we get complete solution, all rational points on the unit circle. Okay, using this kind of idea. Okay. Now let me just stop here and continue on Monday.